Assalamualaikum and good day. So today is the recording of the final parts of the anger modulation, chapter 3. So we're going to resume where we left, okay? So we stop here. So now we're going to continue to the next part of the slides, okay? So today we are going to learn, okay, start with the frequency to amplitude conversion. Means we're going to convert the frequency in terms of amplitude. So okay, let me enable the laser pointer. Okay, so differentiation operation can be performed by any circuit acting like a frequency to amplitude converter. So the conversion is done by a slope detector, differentiator, or discriminator circuits. So any circuit acting like a frequency to amplitude converter. Example, okay, a single tune resonator tank circuit, which is a connected inductor, okay, connected inductor and capacitor act like an electrical resonator. So this is one of your single tune resonant tank circuits. Okay, and then we have a diode detection, one that you already familiar with. We already have almost similar in the detections for the full AM circuits. Okay, so this is the frequency band for linear frequency to amplitude conversion. You see, by the word linear means we're going to have a linear relationship. So you're going to make a cross, you're going to make a straight lines here across one of the gradients. Okay, then you will able to know the frequency, okay, to the corresponding amplitude conversions. Okay, so if you have this transfer function, we call this as a HF, the one that you already learned in signal. Okay, then you make a straight line out of it. Then you're going to have a set of corresponding frequency with a matching amplitude. So we tune at the F naught. However, our F naught is not equal to our carrier frequency. Okay, so here is F2 minus F1 is equal to 2 delta F. Okay, 2 delta F. So it's actually the range of this. Okay, so slope detection using a single tune circuit for frequency to amplitude conversion. So this is the circuit that will perform the conversions. Okay, and this is actually the corresponding graph. Okay, single tune circuit has limited linear region, as you can see, right? We only have this linear region. Okay, very limited, which is not suitable for FM that has large frequency deviation, delta F. So we need to solve this issue. So in order to create a wider linear frequency region for signal with large delta F, okay, we need to use a balanced tune circuits. What is balanced tune circuits? Balanced tune circuit actually we combine two tune circuit with different tune frequencies. Okay, they are combined together. So this is the block diagram, okay, of two tune circuits. So you have tune circuit 1, which is tuned at frequency F1, and you have tune circuit 2, which is tuned at frequency F2. Okay, so this then both of each tune circuit, we're going to go to the envelope detector, similar like what you have here, right? Okay, detection like this, and then they are going to be sum up together. So if you notice, there is a positive and there is a minus here, and then we're going to have V out. Okay, so we're going to have a signal with large delta F, where we're going to have options of wider linear region compared to the circuit that we shown to you previously in the previous slide. So if you see here, this is your tuned circuit at F2, okay? Tuned circuit F2 tune, okay? Tuned at F2 frequency, which is this one, okay? And then this is your tuned circuit 1, which is tuned at F1, okay? So when they are combined, okay, when we combine both of them, okay, plus, we see here minus, means plus and minus. So that's why you're going to have this inverted, right? Okay, because this is being minus. So then you're going to have a wider linear region. So now you have a wider linear region. So frequency, this one is of course frequency to voltage characteristic, okay? So the y-axis is V voltage, like what we have in the previous slides. Next, we go to the phase lock loop, PLL circuits. So by the words phase lock loop here means we're going to lock the phase, okay? We're going to lock any phase. We are going to control the phase we have, okay, whether there is deviation or not. This circuit attempt to lock it, okay. So the phase lock loop PLL for the indirect methods. So you see here, this is our V in, which is our input signal, okay. And then this is our mixer, and this is our E, okay? The difference be error. And then we have a low pass filter, low pass filter, and it goes towards the V outputs, okay, V outputs. And then a similar outputs of low pass filter is going to be feedback to the voltage control oscillator. So voltage control oscillator, the voltage controlling the frequency, okay, voltage control the oscillator, VCO. And then we're going to have VCO that's going to be feedback here and going to be mixed with our V in, okay. So our VCO here is E sine omega CT plus phase naught, okay, plus phase naught in the domain T, of course, okay. So let's see the straightforward operation, okay. The straightforward operation is the phase lock loop is locked to the FC, okay, is locked to the FC, and any deviation from the center frequency will produce voltage in proportion to the modulating signals, okay, which is your VM, okay. The input is FM signal, which here, okay, your input is EC cos omega CT plus phase T. So EC cos omega CT, and we expand this, as you already know, is KF, okay, integration from 0 to T, and our modulating signal, which is the inputs, okay. VCO output, okay, we have VCOT, okay, the output here, okay, is E naught sine omega CT plus phase T, where the phase naught is actually K naught 0T and V naught T dt. Okay? Multiplier in the circuit will function as a phase variation detector. It's referring to this. Okay, we're going to do the phase variation detector. We will detect if there is any phase variation between this VCO and between this V in. Okay, this is basically the multiplier purpose. Okay, function as a phase variation detector. So VE is actually equals to V in multiplied with VCO. So we know that V in is actually a cosine product. Okay, for this basically we assume like that. But in real life, I think you know as well, it can be any cosine, it can be sine, or it can be other sorts of sin. Not necessarily cosine. This is just for the sake of learning. Okay, in real world is much more complex and much more complicated. Okay, so V in is so where were we? Okay, V in is equals to EC cos omega CT. Okay, V in is EC cos omega CT plus phase in, and VCO is our E naught sine omega CT plus phase dot T. So then you implement the trigonometry identity, which is cos A sine B. Then you get this expanded version. So if you can see, there is a higher frequency components that we have here, which is 2 omega CT. And if you refer to the previous slide, we have a low pass filter. So we're going to filter out this high frequency component. So this one is removed. Okay. This one is removed in the together with the others because it is part of this component. So we only have this component instead, which is EC, E naught sine phase in, phase naught T. So we have this as your output of your low pass filters. And then if you see this phase, okay, as we learned from the previous class, okay, so this phase or this phase naught minus a phase in, we're going to have the phase error, if there is any error. So if phase error is too small, which is much less than 1, then your sin phase T will equivalent to your phase. So you can plug in your calculator. Okay. For example, the difference between these two, okay, phase naught T minus phase in, let's say is 0.001. 0.001 means 0.001. So then we press the calculator, sine 0.001. We're going to have so we're going to have almost similar in terms of almost similar. So sine, which when the phase error is much smaller than 1, it can be assumed as just phase error. Okay, so EC E naught over 2 just can be assumed as a sine phase error here. Okay, and then can be assumed as directly as EC E naught over 2 just phase error T here. Okay, this one is actually phi error. So if it's much less than 1, so we can just make it simplified version, EC E naught over 2 with this error. Okay. Next, frequency generated at the VCO, voltage control output, is proportional, okay, to the input voltage of the VCO. So if you see here, okay, the frequency generated at the output here is equivalent to the input, okay, voltage. As you know, right, this one is a voltage controlled oscillator circuit, means we control the frequency is frequency generated at the output is proportional to the input voltage of the VCO. So the phase difference, okay, you see D phase naught, okay, D phi naught over dt is actually K naught of V naught T. Output of the PLN, the phase lock loop, is given as V naught T equals to 1 over K naught d phi over dt. So this is just an integration. We want to do V naught here. Sorry, not integration, is just rearranging V naught. This K naught is bring over here. Then we get the 1 over K naught. So given that the phase error, okay, which is the phase naught minus phase in, is much less than 1, like in the previous slide. So phase in, okay, phase in is actually almost similar with your phase not T, because the difference between these two is much less than 1. Means our phase in here is almost similar to this. Okay, because if you notice, when the two things that is almost similar, when we minus, we will produce the same the value much less than 1. Okay, for example, 3.001 minus 2.9999. Okay, it will produce a different which is much less than 1. Okay, so hence v not t, we output with show here. Okay, sorry for the a bit you know, slight error. Not the slight error, the positioning error just now. That's why I put it away. So hence output after your low pass filter. This one is after low pass filter. V naught t equals to 1 over k naught d phase d phi over dt. Okay, d phi naught here. Okay, equals to 1 over k naught. And they are almost similar, right? Assuming that much less than 1. So this phi naught is equal to your phi in as per here. Okay, and then resulted into this. Then we simplify further. Okay, to kf of kf vmt. Okay, d phi in t is equals to this kf vmt. Okay, and equals to k. So your k here is equivalent to the ratio of your kf. Okay, this one you learned already, over your k naught. Okay, over your k naught. Next, we go to this pre-emphasis and de-emphasis. So the pre-emphasis is located at the transmitter, okay, and de-emphasis is located at your receiver. Alhamdulillah. Okay. Pre-emphasizing the audio for a FM signal is effective because the noise output from an FM system is proportional to the audio frequencies. You see here, pre-emphasize the audio, okay, audio for an F signal. So this is audio, right? Is effective because the noise output from an FM system. Okay, so this is at the transmitter side. So we're going to have output. Okay, is proportional to this audio frequency. Furthermore, the level of the high frequency sound is usually less than the lower frequency. Okay, the level of the high frequency sound is usually less than the lower frequency. So to prevent, the transmitter must increase, okay, the level or the gain of the higher frequency to compensate. Because of our high frequency, the level is usually less than the lower frequency. So the lower frequency usually has higher level. So to prevent this from happen, we need before we transmit, we must increase the gain of the higher frequency in order to compensate this difference of level. So pre-emphasis, the higher frequency are increased in amplitude before being used to modulate the carrier. Means we're going to increase our higher frequency first in terms of amplitude before we modulate, okay, before we modulate the carrier, okay. So therefore it will be less affected by noise. So before we actually modulate them together with the modulating, so we need to increase the frequencies and need the amplitude of our carrier. Okay, so de-emphasis is the mirror of pre-emphasis processor. So this one will be at the receiver. So a 75 microsecond, okay, 75 mu s, okay, 75 mu s pre-emphasis and de-emphasis rule is used in the US. Okay, So what is this is 75 means the rule when we want to use our this pre-emphasis and de-emphasis. So frequency curve where the 3 dB, okay, 3 dB you learn in signal. 3 dB is actually where we have the signal drop to what of the value? Drop or increase by 50% of the values in terms of the sorry, this is not amplitude, this is frequency, okay. So frequency wave curve with 3 dB frequency is at time constant of RC equals to 75. So you know this is how we obtain this. This is actually our time constant tau equals to RC equals to 75. So F is equals to 2 pi RC, and RC is actually equivalent to our 75 millisecond, which is the rule that being used in the US for pre-emphasis and de-emphasis. So you will have this frequency 2120 Hertz. So this is for the 75 emphasis curve, okay, where it is a frequency, okay, as your x-axis and your amplitude as your the deep for the y-axis. So here 2120 is actually your focus or the frequency lah, the frequency 2120, okay, from the resulted from this time constant. Okay, so if you see here, this is your pre-emphasis curve and this is your de-emphasis curve. This is at the transmitter side and this at the receiver sides. Okay, so this is the focus value where the frequency is time constant RC 75 microsecond and converted to hertz. We have this 2120 hertz based on this calculation just now. So this is located at the 3 dB for the pre-emphasis and negative 3 dB for the de-emphasis. Okay. So the pre-emphasis circuits is given by this AF in your signals. Okay. Sorry, my screen turned disappear just now. Okay, so I continue. AF in R1 and R2, then you're going to have pre-emphasis output. So we're going to have this. Oh my god. I'm sharing again. Sorry for that. My monitor, sometimes it's always like often now. It going like off itself. Okay, even though I didn't touch it, and I have always to turn it on again. Okay, so I think this is because I'm using cheap products. Okay, I think this cheap brand so good lesson for me. So pre-emphasis circuits. So this is pre-emphasis output. So you're going to have this at your transmitter side. We're going to put this pre-emphasis at the beginning of your not at the beginning, at the earlier stage of your transmitter okay, section. And this is your de-emphasis circuits. So where you have at the receiver sides, okay, this is going to be at your receiver side. So with the input and RC together, they should produce this 75 milliseconds. Okay. So this is at the transmitter side of your FM transmitter. Okay, this is super heterodyne FM receiver. So at the transmitter side, before modulate we need to pre-emphasize our signals, okay? Where the level of the frequency, the amplitude is increased, okay? As you see just now, we mentioned, to prevent the transmitter must increase the level gain of the higher frequency to compensate. Pre-emphasis, the high frequency are increased in amplitude before being used to modulate. That's why it is before the modulator. So we have this pre-emphasis at our transmitter side. At the receiver side, this is the whole receiver side. So the signal is received here. Then we have an RF to amplify the signal. Like I told you before, the signal sometimes weak in signal because after being travel further distance and after being disturbed by multiple of noise, multiple of fading, pulse phase, path propagation, whatever lah. That's something that maybe of course not covered in this section. So generally the one that we receive is normally weak signal and sometimes weak and not sometimes often have noise, disturbed by noise. Then that's why we need to amplify. So then we have the mixer and IF, our intermediate frequency bandwidth, 200 kilohertz. Then we have limiters and our FM detection circuits. And here we're going to have our de-emphasis. Okay, so it's doing the mirror operations of your pre-emphasis. Then only we go to this audio amplifier. We amplify the audio signal that we receive back, whatever that we whatever transmitted and whatever then we receive, we process, then we generate back. Okay. So this is the radio FM broadcasting. So we broadcast. So if you see for this radio FM broadcasting bandwidth, okay, we have multiple or lots of channel. We call this a channel. So channel 1, channel 2, channel 3, and so on, from 88 megahertz to 108 megahertz. So this is the frequency range, and this is the channel like a slot. And each of them we have 20 megahertz radio FM broadcasting bandwidth. So if we expanded the one channel, okay, we're going to have this. Okay, so each of the channel have their gut band. So gut band is the band where we put in between the channel so that the channel will not overlap. So this is just like macam like safety region so that the channel won't overlap with each others. So if you see here, channel 1, let's say FC1 is 88.1 megahertz. Okay, 88.1 megahertz. Sorry, just now is the bandwidth, 108 minus 88. That's why you have 20 megahertz. It's not the channel. It's not the channel that have 20 megahertz, but it's actually the range here is actually 20 megahertz. Then you divide dependent on the number of channel. Okay. So channel 1, your FC1 is at 8.1 megahertz, the carrier frequency. Then you have 150 kilohertz, okay, the frequency range here of your channel 1, okay. Delta F is plus minus 75 kilohertz, okay. Then you have a 25 kilohertz gut band at the right and another at the left. So you have basically 50 kilohertz of gut band. Okay. And then you have bandwidth 200 kilohertz. Okay, 200 kilohertz, which is the summation of this 1550 kilohertz and your gut band. Okay. Channel 2. Okay, channel 2. Wait, I want to check if it's still recording. Okay. So same for channel 2. So 88.3 megahertz, the same bandwidth, 200 kilohertz. and a gut pain. So information signal range depends, okay? So for the FM signal, if from, okay, for the FM signal, your information signal modulating signal is from 50 Hertz to 15 kilohertz. Please refer back, okay, to your to the slide where we discuss about the difference of the FM signals, FM system and AM system. Okay, please refresh on that. And we have maximum frequency deviation 75 kilohertz, which is this and this. Range of modulation index beta mean 75 kilohertz over 15 kilohertz, which is the minimum. Okay, the minimum is 5, and the beta max is 75 kilohertz over 50 hertz. So you see here 75 kilohertz is the frequency deviation. Beta mean, beta is actually frequency deviation over your FM. So if you want to see the minimum, okay, when we want to have beta minimum means we need to divide it with big number. So logically, so beta delta F, in order to have a big beta maximum, so this one need to be small. So that's why this beta max divide with the smallest possible FM in the system lah, the modulating frequency. Then if you want to this to be minimum, then the modulating frequency should be the highest, which is 15 kilohertz. That's why it's this. So the range of our beta is from 5 to 1500. So per channel bandwidth, we have 200 kilohertz. Okay, this one, which is shown here. Okay. So next, we're going to go to the concept of FM stereo. I think you already were maybe somehow passed through the concept of stereo, right? FM stereo, where we actually have two noise sound source. We have not noise, sorry. We have two sound source, which is of course is left and right. So this is the about this FM stereo. Okay. So the FM super heterodyne receiver shown is monophonic, is one. Stereophonic FM was proposed to make system more natural. So stereo, okay, stereo, FM stereo. This one is mono. Music sound can be affected by space, instrument, etc. Stereo allow reproduction of sound with unique directivity and spatial dimension. The sound from left side reproduced by left speaker and the sound from the right speaker reproduced by right speaker. Okay, so that's why vice versa here. It is important that stereo broadcast should be compatible, okay, should be compatible with mono receiver. Okay, if it's not compatible, of course will be have problem, right? It should be compatible lah. So stereo broadcast should be compatible with our mono receivers. Existing mono should be able to retain the monophonic quality, so it will receive left plus right channel bandwidth with for left plus right equals to 200 kilohertz with the frequency deviations of 75 kilohertz. So this is basically our FM stereo in terms of this transmitter. So please refer to the module for more clear figures. Okay. So we have two information signals. Okay, which is from 0 hertz to 15 for 50 to 15 kilohertz. So this is from the left source and this is from the right source. Then if we go to the summations, okay, summation, or we call it the adder, whatever you use, but it will perform adding operation. So for the first, we're going to have left plus right. Okay. Then if we go to this pre-emphasizer, then undergo this pre-emphasis operation. Then you have A plus R prime. Okay, A plus R prime. Then it will goes to here for the next addition. For this one, the right one, we will have the same. However, it will be minus. Okay, minus left, minus with right. Okay, they undergo as well this pre-emphasizer. Then we're having the L minus R prime. Okay, and then before that, we will put a frequency doubler. Okay, means you doubling the frequency, and then it will undergo the double sideband suppressed carrier modulator. So how this circuit operation, whatever, please refer to your chapter 2. Okay, and then going to here and add it together. So this is the pilot generator. Okay, pilot. Okay, so plus we add them all together. Okay, then we're going to have this FM modulator. Okay, for the FM stereo. Okay, in terms this is spectrum baseband. Okay, spectrum baseband means baseband is your message, right? Baseband stereo signal. Okay, baseband stereo signal. So this is your left plus right prime, which is this. Okay, until your 15th kilohertz. Okay, 0 to 15. And then the next is you have this left minus right with the cos omega ct. Remember, because we have here double sideband suppressed carrier. So you're going to have 23 until 53. Okay, so this is your left minus right prime with and modulated with double sideband suppressed carrier. Means we only need the sidebands. We didn't need the carrier, that's why we don't have that, and that's why we have double, because this is a double sidebands. And then this is your pilot frequency. Pilot frequency 19. So MT is equal to left plus right double prime, which is this, plus L minus right cos omega ct plus cos omega ct t over 2. Okay, so please see the difference. I mean, don't L plus R plus L minus R prime cos omega ct plus cos omega ct over 2. Okay. At the receiver side, so this is the receiver. So emitter discriminator. So we're going to at the receiver when we receive our FM stereo output just now here. Okay, FM modulator. Okay, FM from FM stereo transmitter, then it goes to this FM stereo receiver. So first we're going to have this limiter discriminator, and after that the signal will pass through 3 sections. Okay, one is the band pass filter, and one is the NBF. Okay, narrow band filter, and then we have low pass filter. So low pass filter is from 0 to 15 kilohertz. So this one is actually your FM mono. Then we go to this de-emphasizer. So de-emphasizer at your receiver side, and we put again this L plus R. Okay, and then back to the two system, which is the next for the left source and for the right source. Next, the same signal here that we have from here, we go to this narrowband F, 19 kilohertz. Then it goes to this pilot frequency here. Okay, so then we frequency double, we double the frequency, and from here we have the inputs of the band pass filter 23 to 53. So we only want this frequency here, 23 to 53, and then put here And this, as you know, is the L minus R cos omega ct. Okay, cos omega ct, the double side-base surprise carrier just now, right? And go to the synchronous demodulator. Just now we have modulator, now we have demodulator because it's at the receiver side. So then we obtain our L minus R prime. Okay, then we go to this de-emphasizer. Then we're going to have L minus R again. Okay, then this feedback to the next section and also to this forward part, the continuous part. So in the end, we're going to have 2L plus 2R. So it is a better quality lah, because this is 2L and this is 2R, means like double lah. Because if you see, here is just like L and only R. So that's why it's for better quality. That's why we to make the system more natural. Okay. So we will have reproduction. You see here, reproduction, reproduce. Okay, at the receiver side, with unique directivity and spatial dimension. So there is the advantage and why we want to do this FM stereo. So you have this 2L and 2R. At receiver, FM mono will receive the combined L plus R signal, which is this. Okay. FM stereo will receive L signal on the left and R signal on the right speaker. Okay. So next is the noise in the, okay, we almost finished. Next is we're going to discuss about this noise in FM reception, means at the receiver, not at the transmitter. Now it's at the receiver. So XFM, which is your received frequency modulated signal, after being transmitted over the channel, transmitted over medium, transmission medium, will have a noise addition. So noise is additive in nature, so that's why this is a noise. So the first section, we go through this band pass filter. Okay, we only filter to the frequency range that we want. Okay, because we're going to have mix of signal receive, macam rojak, mix of signal. So we must clear what we want to actually receive lah. Okay, for example, there is many signals. We only take the signals that we intend to receive. There is also signal coming from other sources that we don't want to receive, but we receive it either way. That's why we have this bandpass filter lah. Then we have a amplitude limiter, and we have discriminator and low pass filter. Okay, to remove this high frequency. So then we end up with having this output signal, the one that we want, the information that we want. So power of the output signal without noise. If we didn't have noise, assuming that the limiter is ideal, okay, this one, and remove all amplitude variations. So a discriminator input signal, which is here, okay, can be written as XFM equals to EC cos 2 pi FC plus 2 pi KF VMT d tau. Okay, so this is system without noise. That's why you didn't have the noise component. You only have purely your XFM, then you didn't have any noise. Okay, so this is your XFM, your signals, okay, your signal here without the noise. So that's why we don't have the noise addition. We don't add noise. So instantaneous frequency of the input signal. So you have FIT, okay, instantaneous frequency is equals to FC plus KF VMT, okay, KF VMT. So KF VMT is your discriminator output signal is coming from here, okay. So the power of the output signal is S not T KF VMT. So this is the, if you, the question asks you, right, how in the non-existent of noise if the noise is not present at the receiver side. How you calculate the output signal? So it's actually kf squared Vm squared T lah. Okay. So now we're considering if we start to have noise, which is additive in nature. Okay. So power of the output signal in the presence of additive noise. Okay. So output signal is not. Okay. So discriminator input signal can be written as XFM, and now we have the noise present. Okay. E is equals 2 pi fc plus 2 pi kf bmt d tau. This is your XFM. Okay. Your input frequency modulated signal, and this is your noise. Okay. NCT cos 2 pi fct minus ns sine 2 pi fct. Okay. Then XFM plus Ni equals to RT cos 2 pi Ct minus gamma T. Okay, gamma T. So this is the simplified version of what we have above here. Okay, so phasor diagram of the FM carrier. Okay, see here the FM carrier, the carrier and the noise signals. Okay, so you have EC and NC. Okay, here the carrier noise, and you have NS and SC, and it will make a diagram, an angle of gamma T. So this one here. Okay, this is angle, and is your RT, which is your magnitude. Is this. Okay, so please refer, if you don't remember, refer back to your mathematical concept and basic about what is the phasor diagram. Okay, so here, if you can see, this one will be added together with this in order for us to have your RT, which is this, the recipe. Okay, so instantaneous phase, okay, of the input signal YIT. Okay, instantaneous, so it's not phase of the input signal, is the instantaneous. Okay, so with respect to time, at particular time, but it's not all the time. That's why it's called instantaneous. So is equals to inverse tangent of NST over NEC plus NCT. So inverse tangent of this. For a large carrier power, if we have a large EC lah, so gamma T is equal to tan inverse tangent of this. We remove this NCT in event that EC is very large. EC is very large, that it until this NCT is like negligible, this noise components. So we can put this only EC here. Then we will have instantaneous phase of the input signal equivalent to the ratio of your NST over your EC, the carrier components. Okay, magnitude, carrier magnitude. If we have the large power lah, if we have large carrier power. So discriminator output signals, okay, instantaneous frequency. Discriminator output signal means this here, okay, this output from here. Discriminator output signal instantaneous frequency in the presence of noise. If we have the noise, so omega I equals omega instantaneous frequency equals to the instantaneous phase of the input signal over your dt. Okay, and if you want to have the frequency, it's just over pi, right? So 2 pi f, so that's why you have 2 pi here. D phase input, d differentiation of instantaneous phase of the input signal over dt. So you're going to have FIT equals to 2 pi e s dns over dt. Okay. So how you have this d gamma I over dt is actually coming from here, okay? That's why you have EC component, that's why you have EC here. It's coming from this, okay? So then you have d and st dt, okay? So next is power spectral density, okay? The power PST, okay, of our d and s over dt. So if you recall from your Fourier transform differentiation property in your signal and system, please refer back to your signal and system. So if xt to the frequency domain is xt is equals to xf in the frequency domain, you see here the capital, this is small letters, then d and st over dt is equals to j 2 pi f x f, the time in the frequency domain. So s naught f equals to hf square SIF. So SIF is actually the power spectral density input signal. Okay, power spectral density of discriminator input signal. And S naught F is the power spectral density of discriminator output signal. And this one is a transfer function, as you know, right? So you remember, don't forget about this square. Okay, maybe it's a bit different than what you learn in the linear system, where we have only HF. Now we have this a bit different. So please don't forget about this square. So this is the PST, PST, power spectral density at the input and at the outputs. Okay. Then, so PST, power spectral density, DNST, DNS over dt equals to J2 pi f square times PST of NST. Okay. PST of NST, okay, this one, okay, equals to the N naught. I don't know a bit how to, I forget what is to pronounce this, but I put just N, but it's not N. This one is actually this. The way you write it should be, okay, like this one, okay. Within bands plus minus BT over 2, okay. Then your power spectral density of d and st over dt is equals to j2 pi f squared times this n naught. So power spectral density of discriminator output SDF, okay, the one that produced from the discriminator, is equals to power spectral density of your F instantaneous, okay, Fi, equals to 1 over 2 pi EC, this one that you have just now in the previous slide here, okay, here, equals to 1 over 2 pi EC squared J2 pi F squared times N naught, okay. So here, you have 2 pi EC coming here, okay, and then is here, dNST over dt is what you have here. That's why it is here, okay. You have this, right? Okay, please do carefully try to reproduce them again. Hope you did. You will, understand by going to reproduce it again. Okay. Don't just listen to this lecture and without trying. So it'll be difficult because this is our own mathematics. When mathematics, you need to practice. Okay. After the best band low pass filter, this is restricted in the band of plus minus omega m, because yes, that's the point, right? Using low pass filter, because we're going to remove this high frequency component because our message signal, our information signal is low frequency, right? That's why if we want to know this carrier lah, for example lah, and the noise if is present. Okay, therefore average noise power, okay, and not this one is average noise power at the receiver output is an IFT, okay, is an IFT of SDF, okay. So in case you don't know about this IFT on this card, okay, I think I did open this for you to easy. I put in the Google, not sure. Just now, before I start recording, I search for it so that it'll be easy. Oh my god. Sorry, so my I don't know what happened to my browser. Okay, so if you don't know what this IFT, okay, you just oh my god. You Google lah, because this one is supposed to be known before coming to here. Okay, so indirect okay, you search for this IFT indirect Fourier transform of SDF. Okay, SDF. Here, SD of discriminator is given by SDF. Then after the baseband LPF, after we low pass filter, we restrict to this omega m lah, plus or minus. I think you know already. Therefore, average noise power, which is N naught at the receiver output, is an indirect Fourier transform of SDF. Okay. So N naught is equals to negative W KW, okay, SDF EJ 2 pi FT DF. At T0, okay, so this one is omega, I'm sorry, this one is omega, not W, okay, and N naught is equals to negative M omega M, okay, remember at T equals to 0, okay. So SDF DFT. So at T equals to 0, this component, this one, okay, this part is will become 0 because anything that have the power of 0 become 1, right? So that's why we're only left with this. Then SDF expand from what we have from the previous slides. We have this, okay. Then N naught is equal to eta. I think this one is eta to N naught omega m cube over 3 EC squared. So average noise power at the output, okay, this one is at the output of FM receiver, is actually inverse proportional to your EC, okay, amplitude carrier, okay, carrier amplitude. So if EC is increased, then we're going to have average noise power which is low. Okay, remember this one is the average noise power and not desired means a noise. So it will result in the low of your increasing the EC will result in the reduce of and not, okay, and not average noise power. So this is called this quieting effect. So signal to noise ratio, okay, signal to noise ratio is basically S naught over naught, okay, and this one is at the output. So signal is KF VM squared. So this one we already seen just now. This one, okay, of the output signal S naught over KF naught. Then the noise that we have, which is this one, okay. So it's a ratio, then you will get this, okay. This is only valid if the carrier power is large compared with noise power. Yes, because like what we already assumed just now, this is for the large carrier power F, okay. We are not considering if it's small carrier power is different else, okay, something else. So this one for the large carrier power. So with that, we finish this last chapter, last part of our FM signal. Okay. Okay. Thank you for listening. Assalamualaikum and have a good day.